Today's episode is all about astrobiology. Astrobiology is the study of the origins, evolution, distribution, and future of life in the universe. It also includes the search for habitable environments in the solar system and planets around other stars. It requires a comprehensive, integrated understanding of biological, geological, planetary, and cosmic phenomena. There are three fundamental questions in astrobiology. Where does life begin to evolve? Or more broadly, where did we come from? Is there life elsewhere in the universe? Or are we alone? And finally, what is the future of life on Earth and beyond? Whither are we going? Astrobiology offers us a cosmic perspective. It reminds us of our common heritage and our place in the universe. By studying astrobiology, we can understand life in its cosmic context. We can understand the history of life on Earth by exploring how Earth has been altered by its astronomical environment. For example, the extinction of the dinosaurs is thought to have been caused by an asteroid impact 65 million years ago. We can understand the evolution of stars and a planet's habitability. In our case, when the sun inevitably turns into a red giant star in several billion years, all life on Earth will already have been extinguished and the oceans will have boiled away. If you couldn't already tell, biology and astronomy are inextricably linked from an astrobiologist's perspective. Astrobiology helps us understand the phenomenon of life on Earth, how it came about, and whether it is unique in the universe. The objective, understanding the history and the coevolution of life and the planet. Going even further, understand the evolution of life on the Earth and whether the events and trajectory of evolution is unique to Earth or whether similar or identical events could occur elsewhere. The search for Earth-like planets orbiting other stars might help us understand whether the Earth and its biology is unique, unusual, or common. Detection of rocky worlds around other stars offers us the possibility of a statistical assessment of how common Earth-like worlds are in the cosmos, an analysis of their diversity, and the possibility of determining whether they host detectable life. It also helps us to plan a future for humans on Earth and beyond. Can we establish stations on other planetary surfaces, and will they eventually become self-sustaining? There is also the case of the ancient questions. For centuries, philosophers and researchers alike have been posing questions that remain unsolved to this day. Metrodorus of Chios was the first to propose the atomic theory of matter. Quote, "It would be strange if a single ear of wheat grew in a large plain, or there were only one world in the infinite." Copernicus advanced the heliocentric model of the solar system with his musings. Bruno explored the plurality of worlds. Quote, "In space, there are countless constellations, sun and planets. We see only the suns because they give life. The planets remain invisible, for they are small and dark. There are also numberless Earths circling around their suns, no worse and no less than this globe of ours." Lowell said, quote, "Every opposition has added to the assurance that the canals are artificial, both by disclosing their peculiarities better and by removing generic doubts as to the planet's habitability." With all these historical figures pondering the ideas of astrobiology, it wasn't until the beginnings of the space age that astrobiology was brought firmly into the empirical realms of science. Images returned from spacecraft did not suggest a universe full of civilization. One of the first orbital photographs of Mars, returned by Mariner 4 on July 15, 1965, suggested a dead, desiccated environment unfit for life, and a heavily cratered region south of Amazonas Planitia on Mars. Conversely, water and potentially habitable environments have been found in surprising places. Plumes of water emanating from the south polar region of Saturn's moon Enceladus are just one of the many discoveries that have provided an empirical basis with which to test the hypothesis that habitable conditions exist beyond the Earth. The 1950s and 1960s ushered in new interest for astrobiology. The field was often called exobiology, but this is a more narrow definition focused on the search for life elsewhere. Joshua Lederberg was one such figure at the forefront of exobiology efforts in the 20th century. Gavril Tikhov then wrote the book called Astrobiology and expressed interest in spectroscopy as a means to search for signatures of extraterrestrial life. The interest in astrobiology continues today, with many universities now offering courses, degrees, and research programs dedicated to tackling astrobiological questions. As already mentioned, astrobiology is deeply tied to astronomy and the early universe. To fully grasp astrobiology as a context, it is prudent to also grasp the origins of the universe as it was pre-astrobiologically. This is what scientists have proposed so far. The chemistry of the early universe was not altogether particularly exciting. The chemistry was limited as there were very few elements. The interstellar medium was filled with clouds. Diffuse clouds contained about 100 atoms per cubic centimeter, or 10 to the 8 ions per cubic meter. They hosted H2, a diatomic molecule, and were driven by stellar radiation. Molecular clouds, by contrast, were and are very cold, very dense, and contain about 10 to the 12 ions per cubic meter. These clouds are ginormous, and their chemical composition can be abundant. The gas in these clouds are not ionized, but molecular. Infrared can be used to see through and into molecular clouds. In the beginning, stars formed and promoted nuclear fusion with proton-proton chains. In this chain, two protons must combine. This forms deuterium, which then forms helium-3, which then forms helium-4, and so on. This process emits gamma radiation. Carbon, nitrogen, and oxygen, though very common today, were not present in the early universe. In low-mass stars, all hydrogen in the core is converted to helium. At this point, the core collapses and the temperature of the star changes. This points the star in what is called the red giant phase. This phase is characterized by a helium core and a shell of hydrogen burning. If the star reaches a stage of having a carbon core and helium shell, it will participate in double shell burning. Outer layers of the star are ejected into space. You may have heard this referred to as planetary nebula, but this is a misnomer. The ejection of outer stellar layers is more correctly known as dissipating gas shells. To produce elements heavier than carbon, carbon must be fused. This requires stars with higher masses than low-mass stars, as low-mass stars cannot fuse carbon. High-mass stars are stars whose mass is greater than 2.5 times the mass of the Sun, but less than 8 times the mass of the Sun. These stars are capable of achieving higher temperatures than low-mass stars. They can maintain a carbon, nitrogen, oxygen cycle to produce helium-4. Ultimately, this means 4 hydrogens are converted to helium-4 by way of carbon, nitrogen, oxygen, and gamma radiation. Once the high-mass star achieves a carbon core and shells of both hydrogen and helium, the core can reach a temperature of 600 million Kelvin. Now, carbon fusion can occur to produce neon and so on. Elements higher than iron, though, must be synthesized during supernovae, where there is a huge flux of neutrons. Stars are in danger of becoming neutron stars. A neutron star occurs when the radiation pressure, the pressure created by energy emission, is not strong enough to balance the force of gravity created by the mass of the star. So, the star collapses. Neutron stars may merge to create a supernova. Ultimately, the nucleosynthesis of elements was the result of the Big Bang producing hydrogen, helium, and lithium, cosmic ray fission occurring, the merging of neutron stars leading to the production of heavier elements, exploding massive stars, dying low-mass stars, and radioactive isotopes. The formation of compounds prefers higher temperatures and pressures. With higher temperatures comes faster reactions, and with higher pressure comes more chances for interactions between atoms. Cosmic rays can ionize elements, causing them to interact with other species and form more complex compounds, some of which were complex carbon-containing compounds, the precursors to prebiotic chemistry. H2O, more commonly known as water, was also formed by cosmic ray radiation, though not necessarily in its liquid form. Quasars are phenomena that emit vast amounts of radiation. They are responsible for the production of lots of H2O. Interstellar grains are substrates that enable the adsorption of molecules. They provide a solid base for reactions to occur on, accumulate, and irradiate. At their core, interstellar grains are most likely silicon, or carbon-containing, and they are often surrounded by ices. Molecules may bind to the surface of interstellar grains through a reaction called the Langmuir-Hirshelwood reaction. These grains are important for the formation of larger interstellar objects. While astronomy is important to astrobiology, so is the second part of its nomenclature, biology. A few of the biologically relevant elements are carbon, hydrogen, potassium, oxygen, phosphorus, nitrogen, calcium, and iron. Life on Earth is carbon-based, meaning carbon is the backbone of biological molecules and structures on Earth. Hydrogen is important for transporting protons through hydrogen gradients. Potassium aids in the transport of material through cellular membranes. Oxygen is of course used in respiration. Phosphorus is a key element in the formation of phospholipid bilayers and membranes. The majority of the atmosphere is nitrogen-based. Calcium is vital to shells, bones, nails, and teeth. Finally, iron participates in blood regulation and neurological processes. Biology would not be possible without chemistry. All life, as we know it, uses 6 major elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, affectionately referred to as schnapps. While all 6 elements are found in the molecule from which life is constructed, it is still under debate which elements are actually essential for life. We do know that life on Earth is carbon-based. The atomic structure of carbon is such that it has 4 unpaired electrons in its outer orbit, all available to participate in bonding with other atoms. Thus, a single carbon atom is capable of creating 4 bonds, leading to a variety of bond combinations, chains, and ultimately, molecular formulas. Most biomolecules are polymers composed of repeating units. These molecules can get complex quite quickly, but that is a good thing for us, because life is a complex task, and the execution of complex tasks requires complex molecules. The 4 main classes of molecules for life are proteins, carbohydrates, lipids, and nucleic acids. All 4 molecule classes are made of chains, further solidifying the capabilities of carbon. All these molecules are assembled in liquids, meaning solvents are vital to the chemical reactions of life. Liquids have a finite volume, but their surface area can vary. They allow for ease of movement and interaction among the molecules dissolved in the liquid, promoting chemical reactions. Not all solvents are sufficient for the task of prebiotic chemistry, however, but water is. Water is known as the solvent of life. It has a few characteristics that make it a suitable solvent, its polarity being a very important one. Water has a dipole moment that allows it to readily dissolve both small organic molecules and salts. Salts provide cations and anions that often stabilize other molecules or provide energy sources. When salts are dissolved in water, they separate into cationic and anionic parts, providing charged species for chemical reactions. Small organic compounds can include structures such as amino acids. The polarity of water allows for the dissolution of these small organic compounds, which then leads to water acting as a mediator of organic polymerization reactions. Furthermore, it takes a lot of energy to vaporize water, meaning water reduces the impact of fluctuating environmental temperatures. This high heat of vaporization of water does also mean that the loss of energy during evaporation is high. Biology uses this attribute to its advantage, though, to achieve cooling effects through the loss of energy from evaporation. Therefore, energy loss through evaporation protects against high temperatures in the environment. Another key attribute of water relates to its density profile. Ice, or water in its solid phase, is less dense than water in its liquid phase. In layman's terms, ice floats and provides protection for any organisms that remain in the liquid water beneath the ice. Research is ongoing to further explore the role that evaporation and freezing have in the development of biology from a mechanical point of view. Whether through the loss of water to evaporation or the conversion of water to ice, substituents in the remaining water are condensed into a smaller volume, which may promote an increase in the number of reactions able to occur. Increased reactions means increased complexity. These mechanisms are hot topics for exploring the origins of life in extreme environments such as Mars and Enceladus, but also in places like Antarctica or paleo lakes in present-day deserts. Astrobiology explores many complex questions that humans have pondered for centuries. It is a field with exciting research, animated discussions, infinite imaginations, and vast opportunity. With subfields in geology, astronomy and astrophysics, micro and molecular biology, biochemistry, organic chemistry, and physical chemistry, any scientist can contribute to the field of astrobiology, and in fact, that is what the field needs. More collaborations between previously segregated disciplines will lead to enhanced understandings of the bigger picture, and then maybe we will be able to answer the questions of where did we come from, are we alone, whither are we going, and why am I here?